always do it this time. I go for mine. I got to shine. Now throw your hands up in the sky. Go for mine. I got to shine. Now throw your hands up in the sky.
Welcome to day 2 on our climb up the great mountain of calculus here in our chapter of sequences and series. And we've already spent one day on sequences and we're done with them basically. We're going to graduate on and we're going to talk about some series today. Now just to review, yesterday we said that a sequence was strictly a list of numbers. And we wrote them as, a sub 1, comma, a sub 2, comma, a sub 3, etc., the nth term, etc., to show that it went on towards infinity. Well, today, when we talk about a series, we are now talking about the sum of the numbers that were on that list. Okay? So we're basically, to make a long story short, we're going to replace all the commas with plus signs. So now it's a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot 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 plus a sub n plus dot dot dot. Again, the dot 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 is very important because it just goes on forever and ever. And again, it kind of goes back to our discussion on improper integrals, where we said, yeah, how could you have an unbounded region and then claim that there's a finite amount of area? Same thing here. We're going to add an infinite number of terms together. And at times, we're going to claim that the sum of an infinite number of numbers is actually a finite number. And again, don't think too hard about that or you're going to get a headache. But we do have some shorthand notation here today. Instead of writing all of this, we kind of shorten it up and we say it is the summation. That's the Greek letter sigma for summation. Starting with n equals 1 of a sub n to the infinity, which basically means we're going to substitute a 1, and then we're going to substitute a 2, and we're going to substitute an n, and until, you keep doing that until n hits infinity, hence the upper bound of infinity. Well, as you saw in our subtitle today, up here at the beginning, at the top of the page, whoops, it kind of disappeared. Anyway, it said we're going to continue to answer the same old question over and over again. We're going to continue to ask ourselves, does a particular series converge or does it diverge? And basically converge means that we're going to find that the sum approaches a finite number. Diverge means the sum approaches either infinity or it's one of those situations where it just can't make up its mind and it doesn't really approach one specific number. Now, as we investigate and we try to find the sum of a series, okay, what we're going to do is we're going to create a sequence of partial sums. Sounds kind of wild. We're going to create a sequence of what we like to call partial sums. And that's going to kind of give us a glimpse as to whether a particular series has a pair of converging or not. So, for example, we could say that S sub 1 is equivalent to the sum of just the first term, a sub 1. Now, S sub 2 is the sum of the first two terms. Okay. S sub 3 is the sum of the first three terms. Whoops, I skipped one there. That's a sub 2 plus a sub 3. And as you can see the pattern here, S sub 4 is the sum of the first four terms. Here, a sub 3 plus a sub 4. And at this point, if it's a fairly friendly series, you may start to get a glimpse just by looking at this pattern. You look at what this one equaled and what this one equaled and what this one equaled and what this one equaled, and you may start to see, it seems like the sums are starting to approach a certain number. And of course, we could be real aggressive here and take this on until we get to S sub n, which would be the sum of, the first n terms. Now notice this one actually comes to a period, and then we could continue on in that direction towards infinity and find the infinite sum of the first infinity terms. Okay, our first example tonight is asking us to find the first four partial sums of a given series. And I'll tell you what, my sigmas have come a long way. If you'd have seen them a couple of years ago, you'd certainly get a good chuckle out of them. Perhaps yours are looking rather interesting right now, and just like those squiggly brackets were a few weeks ago, they'll certainly get better over the next week or so. But I'll just get a kind of get a taste for what this series is doing. The first term, if I substituted a 1 in for n, would be 1/2 plus 1/4. Then we substitute a 3 and then a 4, and it looks like we're just going to continue on in such a pattern. And we just want to try to add all these terms up and see if the sum of all of these terms converges towards a certain number. Now, what does your intuition tell you? You'll notice that the terms are decreasing in magnitude. They are certainly getting smaller and smaller. So what you're doing is, yes, you are adding more and more terms, but those terms individually are getting smaller and smaller and smaller, and the terms themselves are approaching 0. So it at least indicates that we have a hope and a prayer of maybe the sum converging to a number. So anyway, as far as partial sums go, we say S sub 1 is strictly the first term, nothing added to it. S sub 2 is the first term added to the second term. Create some common denominators. I think you'll agree we get 3/4. S sub 3 is the sum of the first 3 terms. Again, it could be somewhat of a challenge to create common denominators, but I ended up with 7/8 right there. Excuse me. We want to try to get one more partial sum of the first 4 terms. 1/4 plus 1/8 plus 1/16. Common denominators. I ended up with 15/16. And so what we're starting to do is, without even doing a ton of work, we could say that, boy, do we see a pattern when we look at the sequence of partial sums? And it looks like the sums themselves are getting closer and closer to what? Hopefully you said 1. And what we're going to do is we're going to make the argument that yes, indeed, this series right here equals 1. Okay, so perhaps we just blew your mind a little bit. We're saying we're taking an infinite amount of numbers, we're adding them together, and we're getting a sum of 1. You know what it's really similar to? It's really, really similar to that paper ripping theory we talked about when we did improper integrals. You start with one piece of paper, and you rip that bear in half, and so you just start with one piece of paper, rip it in half again, rip it in half again, rip it in half again. You just continue to do this forever and ever and ever and ever. And then you take everything you've ripped and you add it together. What is the sum? One piece of paper. Okay, at this stage of the game, I'd encourage you to start with a fresh, clean page in your notebook. We're going to talk. We're going to talk about a lot of special kinds of series over the next 3 weeks. And our first one, we're certainly going to start with my favorite. What we consider our friendliest one is called a geometric series. And the generic form of a geometric series is the summation of a times r raised to the nth power. Okay, we're actually going to start at n equals 0. We're going to make a big deal out of that in a little while, but of course we're going all the way up to infinity. Okay, notice, let's put an extra highlight here in our notebooks. We are starting, that's called your index, and our index is starting at n equals 0 instead of 1, and that's very special for geometric series. That's a defining characteristic of them. If we were to expand this particular series out, we substitute a 0 in for n. R to the 0 is 1, so the first term is just a. The second term would be a times r. The third term would be a times r squared, etc., etc. It would get a times r to the n plus, I'm going to squeeze it in. Let's get a dot, dot, dot at the end of yours in your notebook, even though I ran out of room. So that's kind of like the general form, the expanded version of a geometric series. A couple of things. R is what we call the common ratio. Okay. That's going to be extremely important. And just emphasize the fact that if it's a geometric, it starts at n equals 0. In fact, the example we just did a short little while ago, even though it actually started at 1, but it was 1 over 2 to the n, which we could rewrite as 1/2 to the nth power. Okay, that was actually a geometric series, even though we didn't identify it by name. The a value is 1 because there's really no other number there. The common ratio is 1/2. Basically, whatever is being raised to the nth power is your r value. Okay, and we noticed that as we expanded that one out, the terms got smaller and smaller and smaller, so therefore the sum of them together actually had a chance of approaching a finite sum. Now don't misquote that there. Just because the terms get smaller doesn't guarantee that the sum will converge. Now the next example I want to look at, let's consider the series that starts at n equals 0, goes to infinity, it's 3 to the n. Let's go ahead and just investigate this series here. The first term would be a 1, the second term would be a 3, third term would be a 9, fourth term would be a 27, fifth term would be 81, and then 243, etc., etc. Now, what you'll notice here is that the individual terms themselves are increasing. Okay, therefore the sum, as you continue to add more and more numbers, the sum is just really skyrocketing, and the sum is approaching infinity, which instantly means that this series diverges. So basically, if your terms increase, and we'll talk more about this later, and we've got a special name for this, but if the terms increase, it automatically diverges. It has a 0% chance of converging. Alright, I've decided to start, because we have so many theorems to talk about over this chapter, I've decided to go along and number them just along the same way the book numbers them. So this is called Theorem 9.6. It's specific for a geometric series. And it basically says if the absolute value of your common ratio is greater than or equal to 1, like we saw in the last example, our common ratio was a 3, then that series is guaranteed to instantly diverge, okay? No questions asked. If the R value is bigger than or equal to 1, automatic diverge. On the flip side, if the absolute value of R falls somewhere between a 0 and a 1, then it's guaranteed to actually converge. Naturally, you're asking yourself, well, converges to what? And geometric series are super nice because it's one of the rare series that we can tell you exactly what the sum of all the terms is. Unfortunately, the bad news is, and I hope not to burst your bubble too much here, but there's a lot of series down the road where we'll be able to decide whether it converges or not, but even when we say it converges, we won't actually know what it converges to. So this is very special geometric. If it converges, okay, then the sum will always be A divided by 1 minus R. And that's a really special little formula to memorize, okay? And another way of writing that is, again, the sigma is another way of saying sum. So as long as n starts at 0, A times R raised to the nth power all the way to infinity will always equal A divided by 1 minus R. And again, that's only if it converges, then this becomes true. So there's a real special formula to memorize, but it applies only to geometric series. And again, let's emphasize this in our notebook, n has to start at 0. So the remaining portion of our notes, we've got about roughly six examples to do tonight, depending on how we're feeling. But the question's always going to be the same. Does the series converge or diverge? If we say that it converges and it's geometric, which these will be tonight, it is then our job to decide what it converges to. Half the battle tonight is just getting comfortable with recognizing a geometric series. Like I said, we're going to have this big toolbox by the time we're all done. And within that toolbox are going to be several special series and other sorts of tests that we're going to use to determine whether they converge or diverge. And the big thing is when they start to scramble them, it's very hard sometimes just to determine whether I'm working with a geometric or a P series or some other special kind of series. What I want you to do here is, because you have a constant being raised to the nth power, tell yourself that this is geometric, okay? And we're going to rewrite this. The good news is n does start at 0. We're going to rewrite this as 3 times 1/2 to the nth power, okay? I want you to hopefully take time. If you don't believe me, hit the pause button and verify that this expression is equivalent to the one that I rewrote it as, okay? Once you get it rewritten, it's easier to identify that my A is 3, but more importantly, my R value is 1/2. And because that R value is less than 1, we could say that this rascal definitely converges, okay? And what does it converge to? Well, we could say that the sum of this series is equivalent to 3 divided by 1 minus 1/2. And then 3 divided by 1/2 is 6. So not only does it converge, but it converges to a total sum of 6. Okay, here's example number 2. We switched up, spiced it up with a little green color here. Technically, as a mathematician, we kind of feel like we're supposed to cheer for convergent series. We've been kind of brainwashed into thinking that convergent series are the good guys and divergent series are the bad guys, and so forth and so forth. But from a solving perspective, you almost kind of cheer for divergent. They seem to be just less work. It's kind of like once you prove it's divergent, the game's over, move on to the next one. And you'll recognize you do have a constant being raised to the nth power here, so it is a geometric series because of that. Your common ratio is 3/2, and because that's greater than or equal to 1, we're going to instantly say that this geometric series diverges simply because of that. And just to reiterate, your A value was a 1, but that was irrelevant for determining whether it converged or diverged. Okay, our third example, again, this is a very well-behaved geometric series. When I say well-behaved, it's well-behaved because the n value, the index, is starting at 0. I want you to appreciate a problem like this one because they're not going to be this friendly for very long. You can instantly identify that the A value is an 8, and we could identify that the common ratio is 4/5, and because that's less than 1, we'll say that yes, this series does indeed converge. Now, the question is, what does it converge to? Because it's geometric, we can answer that question. We could actually find the sum of it. We're going to say that the summation of this series is equivalent to 8 divided by 1 minus the common ratio. 8 divided by 1/5, I believe, is equal to 40. So just a little bit of mental math there. We're going to add up an infinite number of terms and get a finite number 40. How wild is that? Okay, our fourth example is just slightly messier. It's not in its real clean general form. Just to refresh your memory, we said a geometric series is going to be a times r raised to what power? Yeah, we said r had to be raised to the nth power. Raising it to the n plus 1 power is a totally different ballgame. So what we're going to do first is we're going to do a little decomposition. Okay, decomposition says 3/4 to the nth power times 3/4 to the first power, okay? And then we can clean this up a little bit, and we'll say, well, if we multiply this 2 by that 3/4, we could get something like 6/4, which reduces to 3/2, okay, times 3/4 to the nth power. Now it's just a little cleaner, okay? We can go ahead and we can say, now that we got it polished up a little bit, we could say, yes, the A value is 3/2, the R value is 3/4, and because that's smaller than 1, we'll say that this series converges. What does it converge to, you ask? Let's see. Just a little messier here, but this is certainly, and I think you'd agree with this, this is going to be on the non-calculator section of the exam, A over 1 minus R. Let's see, 3/2 divided by, getting a little messy here. Hopefully you can read this. 3/2 divided by a 4th. Dividing by a 4th, same thing as multiplying by 4. That's going to give me, I think that's 6. If I did that wrong, you can laugh at me tomorrow. Okay, here's example number 5, and here's where it's going to get a little feisty. You'll notice I've given you most of the series, but I did not tell you what the index is. And what I'm going to do here, just to make your life a little challenging, is I'm going to say the index is starting at 1. Okay, I want you to really get aggressive and jump all over that if you see this. This is a big problem, and we've got to address it. We've got to fix it. We have to rewrite this series and where we force the index to start at 0. Okay, so our goal right now is to rewrite it and create an equivalent series that starts at 0. Okay, now when I mean equivalent, friends, maybe expand that first one out. Plug in a 1, and you'll get 3/2 for the first term. Plug in a 2, and you'll get 3/4 for the second term, etc., etc., etc. I want to create a similar series that produces the same first term, the same second term, same third, fourth term, etc., etc. But I'm going to have to tweak this a little bit. Perhaps maybe you have some good guesses on how we need to rewrite that term. Here's my rule of thumb. If we subtract 1 from the index, okay, which we've just done. We went from n equals 1 down to n equals 0. We are then going to add 1 to the exponent. So basically what we're saying is my new exponent is going to be the power of n plus 1. If you're not sure about that, if you're kind of hesitating whether to trust me on that or not, go ahead, substitute a 0 in for that n. See if you actually get 3 halves for the first term. Then go ahead and substitute a 1 into that n. See if you get 3/4 for the second term, so on and so forth. And what you're going to find out here as you investigate that is that the given series right here is perfectly equivalent to the one I rewrote here. We prefer this one because n starts at 0. Why is that so important? If n didn't start at 0, then my little fancy formula goes right out the window and it cannot be applied to the geometric series. Okay, time to scroll down here just a little bit. We'll create a little more room. We're going to hopefully agree that because my r value was 1/2, which is less than 1, that this rascal does converge. Now we're going to go say what it converges to. Okay, we said 3, 1/2. Oh, my goodness. I'm getting ahead of myself. What do I got to do? I've got to decompose that rascal. So we got 1/2 to the n and then 1/2 to the first. If we clean that up just a little bit, certainly the r value stays 1/2, so that part was true. Really what's going to change here is my a value is now 3/2. Okay, and we could say that the sum equals 3/2 divided by 1 minus r, which in this case, let's see, dividing by 1/2 is the same thing as multiplying by 2. I got 3 for the sum. So we saw a real big trick there where we had to force the index to start at 0. We then had to do a little decomposition, clean it up, identify our a value, and eventually get a sum of 3. Here we go, coming down the home stretch here, our big finale for the night. We're going to certainly see some fireworks here. Again, another geometric series. May not look geometric, but you do have constants being raised to the nth power, and by the time we get done working a little magic and rearranging it, I think you'll be convinced it's geometric. Notice I did not tell you the index. We're going to force this one. We're going to say this n is starting at 2. Okay, that's a big problem for us, and we need to address that head on. Alright, I'm going to say I want my n to start at 0. I need to rewrite an equivalent series that has the same first term, same second term, same third term, etc., etc. Our rule of thumb is if you're going to subtract 2 from the index, we're then going to counterbalance that out by adding 2 to all the x or the n values that we saw in the problem. So my new exponent here is n plus 3. My new exponent down here is n plus 2. Notice all I did is added 2 to each of the n values. Next thing we're going to do is we're going to do a little bit of decomposition now. Okay, that's a real popular trend here with geometrics. We could say 2 to the nth times 2 to the third. On the bottom we've got 5 to the nth times 5 squared. Clean up a little bit more. Let's see. I'm going to say this right here is my a value. That's going to be 8/25. Okay, then I could say 2/5 raised to the nth power. Because my r value, or my common ratio, is less than 1, this certainly converges. What does it converge to? Well, we could say that this series converges to a divided by 1 minus r, which is going to be 8/25 divided by 1 minus 2/5. Oh my goodness, check out this number crunching. That's going to be 3/5. Dividing by 3/5 is the same thing as multiplying by 5/3. Okay, let's see, what's that going to turn out to be? I'm getting 8/15. 8/15. So not only does it converge, but it converges to a sum of 8/15. There it is, ladies and gentlemen. There's our brief intro to series. A series is the sum of the numbers that were in your list. A sequence was strictly a list, and that's it. We replaced all our commas with a plus sign, and hence an infinite series was now born. Our same question we're going to answer over and over again. Does it converge or diverge? Okay, and really memorize those formulas, memorize that theorem we wrote down earlier. When does the geometric diverge? When does it converge? Let's make sure we know those two cases very, very well. And we'll tackle some big ones tomorrow. We'll see you.